Good morning. Again, welcome back for lecture number 5, Viscosity, Unit Viscosity for BSc first year physics students. Paper number 1, Mechanics and Properties of Matter. So, in this lecture, we are going to derive Pauli's equation. Pauli's equation, how to derive mathematical expression. Carefully, we have to observe because surely there may be a question in the exam about this derivation. Now let us discuss Pauli's equation. Pauli's equation is a physical law that gives pressure drop in an incompressible and Newtonian fluid in laminar flow flowing through a long cylindrical pipe of constant cross section. Here it is given by volume per unit time, Q or mu. So this is nothing but its expression is pi r raised to 4 pi minus po, I mean inward pressure minus outward pressure, that is net pressure upon 8 mu L. What is L, what is mu, what is pi, what is po, what is r, what is pi, all these things we discuss. Here V, nu is the flow rate, r radius of the tube, outer outlet pressure PO, or sometimes it is shown by P2 also, the inlet fluid pressure P1 or PI, dynamic viscosity of the fluid, viscosity is given here. L stands for length of the tube, length of the pipe which is used for the flow of the liquid. But in order to derive this Pauli's equation, we have to assume some assumptions. Those assumptions are: number 1, the flow of liquid through the tube or pipe must be streamlined, I mean laminar flow. Already we have seen in previous lecture about laminar flow, I mean streamlined flow. Second assumption is the layer in contact with the wall of the tube is at rest, I mean its velocity is 0. Third one is the pressure is uniform over any cross section of the tube. Throughout the tube, pressure must be uniform. And last assumption is that the tube is horizontal so that gravity does not influence the flow. I'll show you picture so that you will get idea about these assumptions. See now, this is a pipe. Here P1 is the inward pressure or PI you take. P2 is the pressure exerted by the viscous fluid. Direction of the fluid is from left to right. It is given applied pressure left to right, that is P1, and pressure from right to left due to viscosity of fluid P2 is from right to left. Net pressure is given here, P is equals to Pi minus Po or P1 minus P2, and this L stands for length of the pipe or length of the tube. Here I have shown you different layers of fluid flowing. This is central layer having more velocity. Velocity decreases, and the layer in contact with the wall of the tube, we have to assume has no velocity, in the sense its velocity is 0. Small r with the radius of the pipe, and this r is uniform throughout the pipe, so that we can say that there is a same pressure, there exists a same pressure on every cross section area, and this tube must be placed horizontal so that there should not be effect of gravity on any area of cross section. Got it? Now, so these are the 4 assumptions you remember for deriving the Pauli's equation. And remember the position of the tube also horizontal. P1 is what, I mean Pi is what, P2 is what, in the sense PO is what, all these things you remember. Net pressure on this fluid is P is equal to P1 minus P2. In some books it is given Pi minus Po. Now let us turn towards this slide. Let's derive the Pauli's equation using dimensional analysis. We have to utilize dimensional method. Consider a fluid flowing steadily through horizontal capillary tube from left to right. Let mu be the velocity per time. I mean volume per time, volume of the liquid flowing per second or per time through a capillary tube. V nu is equal to V by T. This you have to consider. Now, it depends upon what? Volume per unit time depends upon the three things. Number one, coefficient of viscosity, either liquid is thick or thin. Second one is radius of the tube, that is R. The pressure gradient P upon L. I mean the rate of flow of liquid depends upon eta, radius and pressure gradient V by L. Therefore, dimensionally, we see now this volume per unit time is directly proportional to eta raised to A, R raised to B, P upon L raised to C. By removing this proportionality constant, we take a constant, that is K is a dimensionless constant, K eta raised to A, R raised to B, P by L raised to C, say suppose equation number 1. Now what to do? We have to find out the dimensions of these terms. Volume upon time dimensions, L3 T minus 1, M0 L3 T minus 1. It is written like. Then pressure distance is given by M1 L minus 2 T minus 2. This viscosity eta M1 L minus 1 T minus 1, and R is nothing but only L. There is no mass, no time, only L1. Substitute all these values in equation number 1. What we obtain? We obtain, substituting these values, we obtain in left hand side L3 T minus 1, M0. Here M1 L1 L minus 1 T minus 1 raised to A, L B M L minus 2 T minus 2 raised to C. Here M is 0, L is 3, T is minus 1. Here M is what? 1 plus A plus B. Here minus A minus B minus B minus A plus B minus 2C, and T is minus A minus 2C. Got it? Here 2C. Now let's equate the powers of M and L. Equating the powers of M, L and T on both sides, we obtain A plus C is equal to, here is A plus C. A plus C is equal to 0, M power. A plus C is equal to 0, minus A plus B minus 2C is equal to 3 here, and minus A minus 2C is equal to minus 1. If we solve this, A plus C is equal to 0, then A is equal to what? Minus C. Substitute here minus C. What you will get? Minus of minus C means plus C. Here you will get 1C minus 2C becomes minus C is equal to minus 1. Therefore, by solving, C is equal to what we obtain? 1. Substitute the value of C is here 1. A plus 1 is equal to 0 means A is equal to again minus 1. In the same way, here you substitute the values of A and C, we obtain B is equal to 4. Obtaining the values of A, B and C, minus 1, 4 and C respectively, what we obtain? We get, or we substitute the values here. Volume per unit time is equal to constant K, eta, it is A, we have written minus 1, because value of A is what? Minus 1. B is what here? 4. So substitute here 4, R raised to 4, and pressure gradient C is what? Value of C we have seen 1. So substitute here, we obtain 1 here. But experimentally the value of K is shown to be 5 by 8. Experimentally, value of K is what? Shown 5 by 8. So let us substitute volume per unit time is equals to 5 by 8 here like this. Eta as it is. Eta raised to minus 1 is there, so it is taken in the denominator upon eta. R raised to 4 numerator as it is. Here P raised to 1 P as it is, and L is taken below. Already it is in denominator. So volume per unit time is nothing but 5 R raised to 4 P upon 8 N L. I mean, volume per unit time of the liquid is more if the rate, from this formula it is clear that volume per unit time of a liquid flowing through the tube is more if the radius is increased. The radius of the pipe is large, then more water flows through it. The rate of flow of water is more as the radius is increased. In the same way, if net pressure is more, then also volume per unit time increases. Volume per unit time decreases if the liquid has more viscosity. This you remember. As viscosity here in eta is in denominator. So volume per unit time of a liquid is inversely proportional to what here? Viscosity. If the liquid is very thick, volume per unit, I mean rate of flow of liquid through pipe is what? Less, decreases. In the same way, if the pipeline is very short, then also rate of flow of water, rate of flow of liquid is more. If the pipeline is very long, then what happens? As length is L is in denominator, so volume per unit time, I mean rate of flow of water, flow of liquid, flow of fluid through the pipe having more length is less. So I mean rate of flow of liquid or fluid or water through the pipe is dependent on radius, pressure, viscosity and length. Among these, radius and pressure suppose increased, the rate of flow of fluid increases. And remember, if viscosity and length of the pipe is more, viscosity of the liquid is more, length of the pipe is more, then we obtain less quantity of flow of water. I mean rate of flow of water is less. So this equation is known as Pauli's equation for the flow of liquid through a narrow tube, or we say capillary tube. This relation holds good for the fluids having velocities greater, velocities lesser than the critical velocity. Remember, this equation is valid for what? The fluids having velocities lesser than the critical velocity. Because you know, the fluids having velocity more than the critical velocity, it becomes turbulent flow. But in our assumption, what we have considered, our assumptions are that the flow of liquid through the tube or pipe is what? Streamline. So if the flow of the liquid, I mean velocity of the fluid is suppose more than the critical velocity, then it is a contradiction to our assumption that the flow of fluid must be streamlined. Hence, this relation holds true for only the fluids having velocities lesser than the critical velocity. This remember. And this is not only for the fluids having lesser critical velocity, but it should be valid for a pipe or tube which is horizontal in nature, having uniform area of cross section, having same pressure on any cross section area. So in this way, this expression is experimentally derived by using dimensional formula, by using the dimensions. So in this way, this final expression for